Okay, let's unpack this.
Let's do it.
We are diving, I mean, straight into the invisible mechanics of vehicle control.
Right.
The stuff that determines fundamentally if your car stays perfectly straight and predictable.
Or if it suddenly starts sliding.
Exactly. If it just decides to go into an uncontrolled slide, this is physics that's happening. Like every single time you press the gas or tap the brake.
That's absolutely right. And for anyone who gets behind the wheel, this is, it's the fundamental physics of motion management. Our sources really emphasize that we're talking about longitudinal forces.
Longitudinal. So what does that mean exactly?
It just means forces that act perfectly parallel to your direction of travel. So either forward or backward.
Got it.
And these are the forces that determine your speed, your stability, and maybe most importantly, your stopping distance.
And the mission of this deep dive is really to give you, the listener, a practical working understanding of these forces. This isn't just, theory for engineers. This is knowledge that's essential for improving your control, for reducing collision risk, and really for driving with more confidence and skill.
Absolutely. Whether you're in rush hour traffic or, you get caught in a sudden downpour.
Right.
When you understand the limits of how much force your tires can handle before they just surrender their grip, you move from simply operating a machine to truly guiding it.
I like that, guiding it.
Yeah, and this knowledge directly affects your ability to react safely to, well, any sudden situation on the road.
So let's start at that analytical foundation. What exactly are these longitudinal forces? How do we categorize them when a vehicle's moving?
The foundation here is actually pretty straightforward.
Okay.
We can basically break down every forward or backward force acting on a car into 4 main categories.
4, okay.
Yeah, and you can think of it as a constant tug of war.
A tug of war. I like that analogy. So what are the two sides?
Well, you have 2 forces that are inputs, right? The ones you control directly with the pedals.
The gas and the brake.
Exactly. And then you have 2, let's call them environmental forces, that are always there, either resisting you or sometimes assisting you.
Okay, so let's look at those big active players first, the ones the driver's in charge of. First up is the acceleration force.
Right. The acceleration force is the power that propels the vehicle. It all starts when the engine torque gets transmitted through the drivetrain to the wheels, and that's what pushes the car forward.
And in modern cars, especially performance vehicles, this force can be pretty immense, right?
Oh, it's huge. We're talking about generating positive G-forces. The force that literally pushes you back into your seat.
So what's the limit on that force?
It's purely determined by a battle between how much power the engine can generate versus how much friction the road can actually provide.
Which brings us to its counterpart, which is often way more powerful, the braking force.
Yes. That's what slows or stops us. It's our primary safety mechanism.
So how does that work on a physics level?
The braking force is a kinetic force. You're basically converting the vehicle's motion, all that energy, into heat.
Through friction between the brake pads and the rotors.
Exactly. And what's important to realize here is the scale. The research suggests that modern brake systems can generate a deceleration force far greater than the force used for typical acceleration.
Wow, really?
Yeah. They can generate the equivalent of several times the vehicle's weight in resistance. They're designed for immediate, critical deceleration.
That raises a really interesting point of control then. If both of those forces are so massive, how do we modulate them? Especially when we need to stop fast without losing control.
Well, that's where the technology comes in. Our sources all point to anti-lock braking systems, or ABS, as being fundamental to managing that force equation.
Right.
ABS just fundamentally changes how that braking force is applied.
So before ABS, you'd slam the brakes and the wheels would just lock up.
They'd lock solid. And when the wheels lock, they stop rolling, which means they stop gripping. Your tire effectively turns into a hockey puck. You're just sliding.
Okay, so what does ABS do differently?
It works by rapidly modulating the braking force. We're talking hundreds of times per second sometimes. It keeps the braking pressure just below the point of lockup.
So it's constantly dancing right on the edge of the maximum friction that's available.
Precisely. It maximizes your longitudinal braking force while, and this is the key, making sure the wheels continue to roll.
And why is the rolling so important?
Because a rolling tire is a steerable tire. If you maintain that rolling grip, you maintain directional stability, and that's absolutely vital in an emergency.
Okay, so now we get to the subtle players, the environmental forces.
The ones that are always working on your vehicle, whether you acknowledge them or not.
Right. And the first one of these resisting forces is rolling resistance.
What's fascinating here is how misunderstood rolling resistance can be.
People probably just think it's the friction of the tire on the road.
That's what everyone assumes, but that's only a small part of it. The majority of rolling resistance actually comes from a phenomenon called hysteresis.
Hysteresis. Okay, what's that?
It's the energy loss that's caused by the tire constantly deforming and then reforming as it rolls along the road.
So just the act of the tire flexing as it hits the pavement, that creates heat.
Yes, and that heat is energy being lost. It's energy that's resisting the car's forward movement. It's a continuous resistance.
And I imagine a few things would affect that.
Oh, hugely. Tire construction is a big one. Modern radial tires have much lower resistance than the old bias ply tires. And then there's inflation pressure.
Tire pressure.
The sources are really clear on this. If your tires are underinflated, they flex more, which generates more heat, and that increases your rolling resistance significantly.
If we connect this to the bigger picture then, this is really where fuel economy lives and dies.
Absolutely.
I've seen some data suggesting that even a small increase in rolling resistance can have a really tangible effect on your mileage.
It's true. One piece of research I saw noted that roughly a 1% increase in rolling resistance translates to about a 0.5% drop in your vehicle's fuel economy.
That might not sound like much.
It might seem small, but think about it over the lifespan of a vehicle. That constant drag adds up to a serious cost and a loss in performance.
Which explains why you see those special low rolling resistance tires on a lot of EVs and hybrids.
Exactly. They prioritize that efficiency even if it sometimes means sacrificing a tiny bit of ultimate grip. It's an important trade-off decision that engineers are constantly making.
Balancing efficiency against traction. Okay, so what's the last one in our lineup of 4?
The final one is grade resistance. This one's situational, but it can be immensely powerful when it's present.
I think everyone has felt this. You're driving along, and suddenly the car seems to be struggling, but you haven't changed your pedal input at all.
That's it. Grade resistance is purely the force of gravity acting on your vehicle when you're on an incline.
And it's unique because it can work both ways.
It can work for you or against you. When you're driving uphill, you experience a resistance force that actively opposes your forward motion. Your engine doesn't just have to overcome rolling resistance and air resistance anymore. Now it has to literally fight gravity.
So a driver needs to immediately apply a significantly larger acceleration force just to keep a steady speed on a steep hill.
Exactly. And conversely, when you're driving downhill, that force changes direction completely.
Right, it starts helping you.
It actually accelerates your forward motion. Gravity becomes an assist force, so now you have to rely more heavily on your braking force, or maybe engine braking, to keep your speed from just running away from you.
I think we've all been in that winter situation where you're trying to start from a dead stop on a slick, steep hill.
The worst.
You're fighting this massive grade resistance with your acceleration force, but the road is giving you almost zero friction to work with.
It's a perfect illustration of all 4 forces reaching their failure point at the same time. It's the ultimate real-world test.
Understanding these 4 forces then, acceleration, braking, rolling resistance, and grade resistance, it shows you exactly what you're up against and what the mechanical limits of your vehicle truly are. Here's where it gets really interesting, though. We've talked about the forces themselves, but the critical question for safety is, what happens when those forces overpower the tire's ability to maintain grip?
Right. That's the moment you lose directional stability.
And the sources outline 2 distinct ways this can happen.
Yeah, 2 very different and very dangerous ways a vehicle starts sliding along that longitudinal axis, and it's all caused by applying too much pedal for the available friction.
Okay, so let's break down the first one. Sliding due to acceleration. What's the mechanism there, and what does the driver actually feel?
This happens when the driver tries to generate too much acceleration force for the conditions. Think slick, wet roads, or loose gravel.
Okay.
The wheels start spinning faster than the vehicle is actually moving, and that just overwhelms the available friction.
And what's the distinct effect of that? What does it look like?
When the drive wheels lose grip and spin like that, the vehicle loses its directional stability, and the back of the vehicle starts what the research specifically calls fishtailing.
Fishtailing, yeah, we've all seen that.
Think of it like this. Your rear tires are designed to apply a linear forward push, a longitudinal push. If that push becomes erratic because the tires are slipping and sliding, they lose their ability to resist even small side pressures.
And that causes the rear end to swing out sideways.
Correct.
I guess an analogy for the listener might be like pushing a really heavy shopping cart from the back.
Go on.
If you push gently and straight, it goes straight. But if you just shove it aggressively, the back end is going to want to swing out to the side.
That is a perfect analogy. The longitudinal force you've applied exceeds the side force that the tire can generate to keep it straight.
So this immediately answers that critical safety question. Why is it so dangerous to accelerate too quickly in slippery conditions?
Because the force that's meant to move you forward instantly creates an unstable sideways movement.
Okay, let's look at the other side of the coin. Sliding due to braking. This is where ABS is the hero. But what happens when that braking force isn't modulated properly?
This is what happens when a driver applies way too much braking force way too quickly, and it locks the wheels.
And as we said, once a wheel locks, it stops rolling.
And it loses nearly all of its lateral or side-to-side grip. That means you can no longer steer the car, you're just a passenger.
So what's the visible consequence of that? How does it look different from fishtailing?
When the wheels are locked, the car is still moving forward because of all its kinetic energy, but it's no longer pointing where the driver wants it to go.
Okay.
The car frequently loses directional stability and starts sliding at an angle.
So it might slide straight for a second, but then...
But more likely, any subtle difference in friction on the road surface or even a slight steering input you had just before the lockup will cause the vehicle to just skid diagonally, completely out of your control.
That distinction is so critical to remember. So acceleration sliding leads to that unstable wagging motion of fishtailing.
Oh.
And hard braking lockup sliding leads to the directional loss of sliding at an angle.
And in both cases, the moment the longitudinal forces you apply overwhelm the available grip, control is gone.
And this is really where the informed driver can make a difference.
It is. We know that on, say, dry asphalt, the friction coefficient is very high, maybe 0.7 or 0.8.
Right.
But on packed snow or ice, that number plummets to less than 0.2. And that means the total amount of acceleration and braking force you can apply before you start sliding just collapses.
If we connect this to the bigger picture, this kind of specific foundational knowledge is what separates an informed driver from someone who's just, operating a machine based on habit.
Absolutely. Engineers use this exact knowledge, the relationship between these four forces and the friction coefficient to design safety systems.
Like traction control.
Exactly. Traction control systems are basically the mirror image of ABS. They modulate the acceleration force to prevent wheel spin and fishtailing, especially in those low-friction environments.
But the driver still plays the most important role, right? Especially if those systems fail or when the conditions are just really extreme.
The driver is always primary. Our sources emphasize that you can use this knowledge to actively adjust your driving habits. And the key is modulation and smoothness.
So what does that look like in practice?
If you know you're on a slick surface, you have to be incredibly smooth with your pedal inputs. You use what drivers call threshold braking, applying the maximum braking force you can get just before the wheels lock up or just before the ABS starts kicking in continuously.
You're constantly negotiating that limit.
You are. You're trying to keep your force inputs well within the boundaries of that available friction.
So it transforms driving from just a series of stops and starts into more of a continuous conversation with the road surface.
That's a great way to put it.
You're constantly listening to how much resistance the road is giving you, and you're adjusting your force application in milliseconds.
And that's the true skill. A driver who understands that wet roads reduce friction knows they have to be smoother and more deliberate with both acceleration and braking to prevent stability loss.
Right.
They understand that on a steep downhill grade, that grade resistance is helping them accelerate, which means they need to pre-apply more braking force just to maintain their speed.
So what does this all mean? Let's bring it all together.
Okay.
Our core idea seems clear. Managing your acceleration force and your braking force is absolutely essential to prevent skidding and maintain stability.
Especially when road conditions are poor.
You control the input, but the physical environment dictates the maximum safe force output.
And that leads us to the final and I think provocative thought here.
Let's hear it.
We spend so much time and energy focusing on the forces we actively control, the gas and the brake.
Right, the pedals.
But what our sources show us is that real vehicle control is also about constantly managing the forces we don't directly control. That rolling resistance and that grade resistance.
Those quiet, continuous forces that are always eating up your fuel or demanding extra brake pressure.
Exactly. They are acting on your car continuously, quietly working against you, or sometimes with you. We often ignore them, but they are constantly demanding that you adjust your pedal input to compensate.
A smart driver isn't just stomping the gas then.
No. They're calculating, often completely unconsciously, how much extra acceleration force is needed to overcome that slight incline just to maintain momentum. They know that their tire pressure setting is critical to managing that background drag from rolling resistance.
So that's the constant, subtle calculation a truly skilled driver is making.
It is. They're accounting for the invisible drag and the push of the environment, and they're adjusting the longitudinal forces they apply to stay safe and efficient.
Yes, the takeaway for everyone listening is,
Next time you accelerate or you brake, just for a second, think about those 4 parallel forces at work. Are you simply fighting gravity up a hill and the drag of your tires? Or are you applying so much controlled force that you're actually dancing on the very edge of a skid? Understanding that balance, I think, is the true key to control.
be aware of those invisible parallel forces. Drive safe, and we'll catch you on the next deep dive.
Please like, subscribe, and get notified.